he's Colin.
Can we undo it and can we go back into practice mode for a couple of minutes? Okay, we'll just wait one more minute to open. While the doors are open, we'll start in another minute here.
Stimmt.
Okay, it looks like it's time to start. So welcome everyone. Today is the last session of Tuesday, and this is a session on negative effects. So we'll have 3 presenters in this session. So we'll just go ahead right on in and start with the first presenter. So our first presenter is Jan Gründling from University of Trier. And the paper is Answering with Bow and Arrow, Questionnaires and VR Blend Without Distorting the Outcome. So welcome, Jen, and please go ahead and start when you're ready.
Okay.
Thank
you, Barrett.
Sorry, Jen, my mistake. There's just a couple of business items to get out of the way. So I just want to remind everybody who's in the attendance. We invite you to ask questions. So please, save all your questions. All of the questions will be at the end of the session. So we'll have the 3 presentations in a row, and then we'll have the Q&A at the end after all of the presenters. If possible, please present your questions in the Discord channel for this session. That's preferred. If you can't post them there, you may use the chat, but please, if you have access to the Discord, put them in there, and we'll save the questions and we'll come back to them at the end. So sorry about that at the end. So please, pardon my interruption. Please go ahead.
Okay, thank you, Barrett. On behalf of my co-authors, I'm presenting our work on questionnaires in VR and their representation. And I'll start right away. So when psychological factors such as presence are assessed by questionnaires, the measurements may be influenced by variables like a break in presence induced by transitioning between physical and virtual reality or time elapsed between the actual sensation and its measurement. However, moreover, participants of previous experiments stated discomfort due to changing repeatedly between VR and non-VR, which motivates the investigation of new ways of administering questionnaires in VR research. Previous attempts to integrate questionnaires into a VR as world or user-anchored canvases still lead to a clear separation between the interaction for the task and data acquisition in the virtual environment, which has been shown as problematic due to the interruption of experience.
Sorry, Jan, it looks like, I wasn't sure actually, but it looks like we're not...
I forgot the screen share. I'm very sorry. Yeah. Okay, so...
And I just wasn't able to see it from my view, but that's much better.
Yeah.
Thanks, please.
Right.
And thanks for Tobias for mentioning.
Should I start over or just continue from this point?
I think we have, we're kind of short of speakers in this session, so I think we have extra time. So I think just go ahead and start from the beginning.
Okay, then I would just do a quick run through the first 2 bullets. So there's not much to see on the slides. So this was for the first few sentences. The bullets for psychological factors, previous experiments that stated discomfort due to changing repeatedly between VR and non-VR, and which is the motivation to search for new ways of administering questionnaires. So previous attempts to integrate questionnaires into VR as world or user-anchored canvases still lead to a clear separation between the interaction for task and data acquisition in the virtual environment, which has been shown as problematic due to the interruption of experience. A deeper integration into the virtual environment and interaction concept could resolve this issue, and therefore the question arises how questionnaires can be integrated as deeply as possible and seamless as possible into a VR application to avoid breaking the experience without blurring the questionnaire results. For a serious PC video game, Frommel and colleagues developed an approach to include the questionnaire as a playable element into the game, finding that it produces differences in questionnaire scores compared to a screen overlay questionnaire as showed here on the right. Safikani and colleagues investigated a similar embedding approach for VR with a specific focus on the usability of the embedded questionnaires. However, the findings about the influence of different questionnaire modalities on their respective questionnaire results appear to be ambiguous, as some studies find that the results are biased by the type of presenting the questionnaire to the participants, while others do not. Because of this ambiguity, we hypothesized that presence, workload, and satisfaction questionnaires lead to different results when they are mapped onto virtual world elements and interaction methods compared to text panel or PC versions. For the implementation used in this work, two cases of answering items have been considered: the liquor type item and a continuous scale item. And we chose a scenario of an archery task as a virtual environment. Accordingly, a bow and arrow interaction style was chosen, fitting the task, which I will describe later. Thereby, the mapping represents a one-to-one mapping of the interaction technique used for the game to the one for answering the questionnaire. So now I will show what the scales look like. For the liquor type items, the answering options were shown as symbolic targets, as you can see here, which were placed in a semicircle around the user. And by shooting on the numbers, the user can choose their answer and confirm by shooting at the check mark above. Okay, so for the continuous scale, this looks a bit different. We had this slider-like representation, which we had to adapt somehow. And as a best fit, we vertically extruded semicircle used and placed it within the participant's field of view and displayed the answering values on the surface. And again, it was rated by firing at it and confirming with the check mark above. So the hypothesis mentioned earlier assume a difference in scores of questionnaires depending on the form of integration into virtual reality. To test for this hypothesis, an experimental design was set up, aiming at comparison of mean questionnaire scores. And this was a 1 factorial design with repeated measurements at 3 levels. And so the questionnaire modality as an independent variable denotes 3 distinct forms of the same questionnaire in terms of presentation style and manner of data entry, which is classic VR text and VR game. For the required sample size was calculated aiming at an 80% probability of revealing an effect if existent, and this led to 36 participants in the study, 16 female, 20 male, with an age range from 18 to 54. There was an introductory phase where when people once entered the laboratory were welcomed and asked to fill in some demographic questionnaire, and after an instruction on how to use the bow and arrow, the virtual bow and arrow, The participants were asked to do the actual task, which looks as follows, hopefully. Okay. So they were placed in an open environment with a bow and instructed to shoot arrows at targets emerging in the scene randomly after an introductory phase of 3 targets. So later on, the targets also began to move, which made it a bit more difficult. And the phase or the task ended after a specified time period to ensure a set length for the overall study time. To test for the differences in mean score statistically, we used a parametric bootstrapping approach with 10,000 iterations, and we found no differences in questionnaire scores identified across modalities. So to conclude, we needed to reject all 3 hypotheses of this work, which suggests that the deep integration of questionnaires can be implemented in virtual reality without having to fear that the quality of the data they collect will suffer. Thank you for listening.
Sorry, that's muted. Thank you, Jan. That was great. So we're just going to go ahead. Again, we'll please put your questions in the Discord chat, and we're going to save those for the end. But we're going to move on now to our next presenter. So next up is Daniel Zielasko, also from the University of Trier. And Daniel is going to present systematic design space exploration of discrete virtual rotations in VR. Please take it away, Daniel.
My name is Daniel Zielasko, and today I want to talk about discrete virtual rotations in virtual reality. Relying on physical rotations should be the goal of every virtual reality application, because the virtual counterparts come with a number of disadvantages. The maybe biggest is that the induced mismatch between the visual and the vestibular system are potentially raising cybersickness. Also, the user's spatial awareness can be negatively influenced, and it's less natural. So, why are we talking about virtual rotations here at all? There are many scenarios in which physical rotation is limited or not possible at all. Some of them are depicted here. Okay, then we have to tackle the challenges that virtual rotation comes along with. A solution at least to cybersickness can be teleportation. The method is widely adapted, and its discretization of motion can also be applied to rotations. As we can see here, the viewpoint orientation is jumping. Discrete virtual rotations are already researched, for instance in the work of Salgunam and Dragon. In these methods, the users specify a direction, left-right, and then their viewpoint is rotated in this direction instantaneously. Faumani and Tether implemented rotational snapping, a hybrid method. When searching for a translational sibling, there is for instance dashing, where the users specify a direction with their viewpoint orientation and then move into this direction very quickly. However, the majority of teleportation methods use target selection, not directional input, and thus the question arises if there's also a pendant in virtual rotation, something like a rotation selection method. There's actually work that investigates orientation selection together with the target selection process of target-based teleportation. But we did not find any work that deals with egocentric orientation selection. This observation led us to the point where we wanted to have a more structured view on different virtual rotation techniques. We constructed a classification. With respect to the limited time, we unfortunately can't discuss it now and have to point you to the paper or ourselves after the talk. For now, we need to know that we identified 3 dimensions: continuity, being a scale between continuous and discrete, target acquisition with the classes directional and selection, and finally body-based, also not being binary. At the end, there are some gaps in the table they do span, and this might be for good reason. restricted to discrete methods we wanted to find out with this work. To do so, we implemented 2 by 2 equals 5 representatives. 2 discrete and directional methods, both executed rotational jumps of 11.25 degrees every 0.4 seconds at maximum. In the controller-based method, the directional input came from a joystick, and in the body-based interface from a left-right movement of the upper body. All interfaces were used seated. For the rotation selection, we initially implemented 3 methods. 2 controller-based versions, one using the handheld controller as a pointing device, the other using the joystick to define a direction. The latter worked comparable but was not preferred by the users, so we will leave it out in the following. With the body-based technique, the target orientation was selected with the upper body leaning into the desired direction. We conducted a remote user study. In the experiment, the participants had to perform a primed and a naive rotational search task. Both tasks were conducted in a semi-random generated virtual environment like the ones depicted below. For the primed search task, we used and slightly adapted a design created by Langben et al. Here, the participants repeatedly had to find a target cube behind them, and at the start, an arrow showed them the direction they have to search in. When having accomplished that, participants were asked in which direction they started in. We added a rapid pointing task here to reveal potential effects of lower cognitive spatial orientation. The naive search task was inspired by a design of Freitag et al. Here the participants had to find specific objects in the same scene. Let's directly jump into the results and have our first look at the factor of body-based interaction. As expected, the body-based methods were slower in task performance than the device-based methods. But we further also not found a significant advantage in spatial orientation. Maybe most remarkably, the SUS scores of the body-based methods were lower as well, especially for the body-based selection method. We already mentioned that the degree of embodiment is not binary and likely multidimensional. Thus our findings can only be a first indication and not cover the whole design space. Moving on to the factor target acquisition. We do see the absolute pointing error of a first rapid pointing on the left and of a second corrected pointing on the right. And as expected, the selection-based methods provoked a significantly higher absolute pointing and configuration error in the rapid pointing. However, this effect vanished in the second pointing, where people had time to correct their input along landmarks and so on. Last and maybe most interesting, the task performance looked the following. On the left, there are the results for the primed search task, and on the right, for the naive search task. As expected, the selection-based pointing methods were faster in the primed search task. Surprisingly, the exact same pattern is mirrored to the naive search task as well. One observation that we made that can explain the results is one remarkable positive trait of selection-based techniques is they can be used as directional techniques with variable jumping distance, which also means there is also no parametrization. And participants in part did exactly this. We have to add that in this study we had an isolated view on virtual rotation, while in reality most of the time rotations come together with travel and it's questionable in how far results transfer. We talked about parametrization. Especially the directional methods rely on parameters, and while most of them were tested empirical before or were based on related work, this is still a factor. For future work, we found that selection-based virtual rotation works well, and we want to have a deeper look into this. We already started to investigate the method being included in a regular travel interface. That's it for now. Thank you for your attention.
All right, fantastic. So once again, if you have questions for Daniel or for Jan, please post those in the Discord channel, and we'll get to those at the end after our final presenter. So last but not least is Colin Groth from the Institute for Computer Graphics at TU Braunschweig. And Colin is going to present his paper, Omnidirectional Galvanic Vestibular Stimulation in Virtual Reality.
Thank you. Can you hear us and see our screen well? Yeah? Okay.
Oh, good.
Okay, thanks. Hi, I'm Colin, and today I'd like to tell you why low electrical currents may be a solution against cybersickness. And you probably all know that VR today is quite known. It's fun. You can play Beat Saber at the weekends. But if you then switch to maybe a holiday video, 360 video in VR, where the content is moving, you quickly get sick. That's a known phenomenon that is called cybersickness. And cybersickness seems to rely mostly on a mismatch between what you see and what you feel with your body, because if you watch this video, you stand still most of the times, but you see this extreme movement and your brain doesn't match this up and you get sick. So a common way to fight this cybersickness is implemented by blurring out the outer regions or fully blending them out so that the visual movement is not so strong and it better matches with what we feel with our body. But this can also reduce the presence within the scene. So we want to look at a different approach here. Instead of reducing this visual movement, we use a technique called galvanic vestibular stimulation to stimulate the vestibular system so that the participant who has the glasses feels this virtual movement. So it really feels like the person is moving, but he's sitting on a chair. Sounds like magic now, but it's actually a quite known technique. As I said, GVS, galvanic stimulation, short GVS, and it describes the direct stimulation of the galvanic system. So the system we have in our ear, where we can sense rotations and movements in the world. And it uses low electrical currents, which may sound dangerous now, but it's actually a quite known technique and has been used a lot in medicine for over 20 years and from the military, NASA. So it can be considered harmless. There has been some work before with GVS in computer graphics, but not too much. And the works we can see in the literature mostly deal with two electrodes, so the two behind the mastroids, and accordingly one axis of stimulation. But I mean, you all know that VR content is not only moving in one dimension, so these models have their limitations. Let's take another look at a non-VR related work of Svet et al. That presented a different model called OVR. They used not only 2 electrodes, but 5. And with this 5 electrodes, it was possible the first time to not only stimulate one axis, but to stimulate either yaw, pitch, or roll at one point in time. And we took a look at this OVR-based stimulation and adjusted to virtual reality. In particular, we took a look at 2 different methods. So first of all, stimulating either yaw, pitch, or roll, according to the method that Svet et al. Already presented. We call this the strongest axis stimulation because at one point in time, we only stimulate the strongest of yaw, pitch, and roll. Yeah, that's the strongest in this frame. And the second stimulation is a stimulation we want to present here. We call it the interpolated current stimulation. It stimulates all roll, pitch, and yaw rotation that are present at a certain point in time simultaneously. Let's take a closer look at this type of stimulation. So for the interpolated current stimulation, so first of all, you have to know that with OVR, all rotations from the single components are represented by one pair of electrodes. There are multiple options for your pitch and roll, but there are always 2 electrodes. And if we want to stimulate more than one rotational component, let's say, for example, we have a yaw and a slide pitch at the same time. Then we take this yaw component and we take this pitch component and combine them. Of course, we also weight them according to what is stronger present in the actual rotation. For this combination, you have to know that due to these multiple options we have, there can happen some negative influences that are also prevented with the formulas presented here. Okay, now we know what we do. What you have to know also is that the 360 videos we used in our experiment have different movement speeds. So we adjust the stimulation according to the movement speed in the video. And we also compute the stimulation on runtime. So not before, on runtime, depending not only on the movement speed in the video, but also the look direction of the participant. Okay, here you can see how we designed our experiments. So we used counterbalanced conditions. So we used counterbalanced conditions and within subject experiment with 3 sessions. So you have first of all the 2 GVS sessions and the third control condition where we attached the electrodes but didn't say that to the participant that we didn't put any stimulation on the electrodes. Here you can see the 2 stimuli. So we have the walking scene and a biking scene. They are played directly after one another. We have 10 minutes video in total and 47 participants. For the feedback, we use 2 techniques. So first of all, the very well-known SSQ, Simulator Sickness Questionnaire. And to have a live feedback, we also gave a handheld controller to the participants and asked them to press a button every time they feel more or so they feel worse or less worse, so better. And we use this for a live tracking of the discomfort rating. Here you can see again how the electrodes are attached. So we have 5 electrodes, 2 on the mastroids behind the ear. We have 1 on the forehead and 2 in the neck. And what is also very important is to perform a calibration step, because we found that people are very different, have a very different sensation to electrical current. So when one isn't feeling anything, the other person is already laying on the ground. So you have to adjust this level of stimulation to the individuals you perform the experiment with. And this maximum current that is found at the calibration is never exceeded in the experiment for ethical reasons, obviously. Okay, let's take a look at the results. The results show a clear trend, as you can see here. The control condition is on the highest levels from the simulator sickness score. And both GVS methods were able to equally reduce this sickness score significantly. For the interpolated current stimulation, there were also some other positive side effects. If we look at the times participants were willing to stay in the virtual experience, we can see that they stayed the longest with the interpolated current stimulation that was also significantly higher than with the control condition. Okay, let's take a look at the discomfort values. These are the values from the live feedback from the participants. So over time, you can see first the walking scene and then the mountain biking scene where most of the sickness is happening because there are the strongest movements. And we can see identical results. With the galvanic stimulation, the level of discomfort is on a much lower level. And we can achieve a significant reduction here. What we also see is that it progresses slower and more constant. And what is also important to note is that discomfort, we specifically asked them not to just rate cyber sickness, but to rate any feeling of discomfort, so also negative feelings that arise from the GVS itself, like itching. And we can see that this is not so much the case. Again, we also know that VR is a subject to gender bias. So we investigated all results independent for men and women. And while both GVS methods achieved a significant reduction for both genders, you can clearly see that the results for men are much lower. Counterintuitively, we also found that although the results were on the lower level for men, they also stayed longer in the scene, what was quite unexpected. Okay, let's have a quick summary. So with our work, we like to introduce a sensation of rotation in arbitrary direction. And from the results, we can see that a significant improvement of the virtual experience is accomplished. Thank you so much for your attention.
Super, thank you, Colin. So let's give a hand, first of all, to all of our presenters. Thanks very much. Some great talks. And I guess we'll move on now to the question phase. So I will start, maybe going back to the first paper. So there's a question for Jan from Jacob Young. So the question is, with the continuous scale, did you consider how participants' aim might affect the quite literal accuracy of the responses they gave? So, so go ahead.
Yeah, so we did not directly assess how accurate they are or how satisfied with the accuracy they were, but it didn't take much more attempts than 1 or 2 for the participants. So, but this this is from my memory of attending the sessions.
Yeah. So I guess that kind of
interesting thought
answers the follow-up question from the same question, also from Jacob. Did the people need multiple tries to give the desired answer?
Yes. So yeah, some did, yes. But what we also have seen is that people try out how to so shoot at random points on the scale to just try out the functionality, which does not really allow to count this as as a rating for the accuracy, because we would then have to identify when they really want to answer the question with which one of the shoots.
Yeah. So they're having too much fun, and the questionnaire is interfering with the fun.
To some extent, I would say.
I was curious about this too. So did you make the difficulty much easier for the questions than it was doing the normal task, or was it kind of consistent, or did you have to make the targets a lot?
You mean you're talking about the task difficulty? Or?
Yeah. So for the questionnaire, did you make the targets easier to hit for the questionnaire?
Well, yes, in that point that the flying curve of the arrow was straight and not for the you would be able to shoot them straight rather than having to calculate the parabolic flying curve of the arrow. But this is also due to the targets being placed much nearer to the user than the targets in the task.
Got it. Yeah. So it does change a little bit. So I guess
yes,
taking that, to the extreme. Say if you had a very challenging game experience where it was very difficult intentionally to hit the targets, and then you maybe need to make this much easier for the questionnaire. So I guess in a way this would require you to change the task to some extent. So I guess the question is, how important is it to kind of keep that consistency between the task and the questionnaire? Can they What do you think it would have a large effect if you changed to a different task?
That's a good point. Well, actually,
Or say
so that would mean that to adjust for or to adapt to the questionnaire representation, we would have to place the targets equally distant as the targets in the questionnaire item. But yeah, actually, I don't know if this difference in task shooting and questionnaire shooting has a difference. Possibly.
So I guess I'm wondering, say, for instance, if you had a task that was quite different than shooting targets that didn't really adapt well to a questionnaire, right? So say some continuous, well, I guess the continuous scale maybe isn't a good example, but I think you know what I mean. So I guess your assumption though is that there's some continuity between the two that adds to or prevents the break in presence.
Okay, yeah, no, I get it. Yeah, no, you mean a completely different environment, for example. So I think I would go then for embedding this in, for example, if you have to have in a task where you have to run around in the world to solve riddles, for example, just what comes to my mind. I would then go for embedding the questionnaires in that environment as interactable objects. This is also what Safikani and colleagues did in a similar way. So if there is the interest.
Makes for an interesting design challenge, I guess. Yeah, okay, maybe I will come back to you. Yeah, there's another question, but I'm just going to mix things up a bit. So I'm going to move to a question for Daniel. Daniel, we have a question from Marco Somalnian. Apologies, Marco Somalnian. The question is, do you have any insight about the reason that the SUS scores were worse for body-based rotation? So any thoughts about the reason behind that?
Yeah, a lot of thoughts, but maybe let's keep that. I try to find a short answer to that, and when you are interested in more, approach me afterwards and we can discuss that. But I think, so one thing is, as I just shortly mentioned in the talk, this whole topic about embodied interaction is just scratched in this research endeavor, right? There are so many ways you can implement embodied interaction to the process of target selection or whatever, and we just picked this one because of multiple reasons. For the directional one, it's somehow maybe intuitive to do this left, right, and you are turning, and there were, in related work, it's already done comparably in travel interfaces, so we decided for that, and thus we took a comparable one for the selection. And I think, so that was the reasoning. It was not that it makes sense from it was because of related work and what's there already, because we have to start somewhere. And I think when you think about the task, you constantly, especially when you want to select the direction, you constantly have to lean back, because that's usually where the targets are. And I think people don't like that much. And another reason in the same direction is you had to maybe even lean backwards multiple times, because what we did here, we decided to not implement a hybrid interface. So what you could do, you of course could lean back and implement a dwell time, after which you are turning again, right? Then you could do something like I lean into this direction, and after half a second, I'm turning constantly into that direction, allowing hybrid use of the method. And I actually think that's a better idea to do so, but we wanted to keep methods pretty clear here. And especially in the embodied versions, I think there's a lot of room to try out more. And why I'm saying that, because while we found pretty worse results or bad results, especially in usability for the embedded, for the implemented methods, when you think about this, and we also discussed that in the paper, this pointing process where you use a controller to point and click, that's pretty embodied already, right? We considered it here to be non-embodied because of simplicity, but we had this pre-study. It was not really a pre-study because the other condition was also in the study, but we left it out for simplicity. We had this comparison to a joystick versus pointing, and of course that's a big difference in embodied interaction, and the pointing has won this battle. So I think there's much more to this topic, and there's more research needed on that one. And in particular, it gets interesting when combining it to travel interfaces, because I'm doing a lot of leaning interfaces for travel, and there it's also more difficult to use it for rotation and for translation. And that's one reason why we also tested this, right? Do you want to use leaning for the rotation part or for the translation part? And maybe we go for the translation part now and check out how that's going. Hope that answers the question somehow.
Yeah, I think, well, if not, there's certainly room for discussion afterwards, but I think you're right, it's actually really an interesting question. I think, you know, there's a couple of things. So what came to mind for me is maybe there's just this large body mass that, you know, Bill Buxton talks about, you know, how larger limbs to have a slower reaction time, and I guess this is, you said in the paper, this is to be expected. But I'm kind of wondering if that's, you know, maybe that's not the primary thing, right? So if when you're talking about translation, so in Doug Bowman talks about this idea of naturalism and you know, trying to recreate, you know, using leaning to say navigate forward. And so I was kind of interested in this idea of translation and how to use these together. But first, I guess, do you think the SUS matters? Maybe it's a little bit less usable because it's slower, but does that necessarily mean it's less pleasant? And then before I'll just ask my second question for you answer that. How can you talk a bit more about how you would combine rotation and translation together? Because I think that's a really interesting problem.
I indeed think it matters a lot, because what you can see in the results is, especially in the performance results, often that we are pretty good to adapt, right? Humans are super good in adaptation, and often you have really bad interfaces, and surprisingly participants are okayish, or you don't even find a difference. And I think in these cases, you reveal these bad interfaces, for instance, by ZUS. I think sometimes that's really possible, because then you really have big differences in the ZUS scores, and the performance criteria are okayish, right? There are also other cases where you can make the hard decision on that, but in this case it was pretty obvious. And I think then this is especially interesting for on the long run, right? People would maybe just stop using that interface. They can adapt to it and they can use it, but they don't want to use it. So I think that's pretty important in these cases. Yeah, combining both interfaces, so really using it as a travel interface, that's an interesting question, and we as I said, we are trying it out at the moment, and I cannot say too much about it, because the idea first sounds very interesting, but then you encounter some interesting questions, and there are a lot of options how to combine those two. And at the moment, I'm not sure what are the best. So we are just prototyping it at the moment and see what works.
Sure.
Yeah. So.
Okay. Yeah, that's interesting. And I guess there's also combinations when you start thinking about, you know, one maybe translation could be discrete and rotation continuous, and vice versa, and so forth.
Yeah.
Great. Thanks for the great answers. I'm going to move to a question for Colin. So this question is by Tobias. Tobias, since you have access to your mute button, would you like to ask the question?
Oh yeah, I can do that. Yeah, first of all, thanks all for the great talks. A question for Colin. You so basically for the galvanic stimulation, you said that it's you need to individualize that. You mentioned that. You said basically that the range is per participant differently. And you said you need to do this for ethical reason. My question is, how do you calibrate it ethically? So how do you find the right response or the right thresholds ethically? I'm not sure if you have an ethic board or something. Yeah.
It's actually quite easy. So we start at the lowest current, so basically 0, and then go up really slow steps. And then we ask the participants all the time, like, do you feel something? Do you feel comfortable? And if they start to say, no, it's not so comfortable anymore, we took the value that is below that and say that's our maximum. So we never exceed that in the experiment, and then scale all the stimulation in the experiment so that the maximum fits that found value. So yeah, that's basically what we do.
Okay, yeah.
So for maybe a little bit of context, so I'm the second author, sorry.
So I guess so.
Usually there's
do you want to introduce yourself, second author? You say your name?
I'm JP. I'm Jan-Philipp Tauscher on the paper.
Okay.
And so there's usually a higher threshold that's being used in GBS, and our device is way lower. So our device can only go up to 2.5 milliamperes, which is compared to other simulator studies very low. And so we are only going up to that value because that's the only thing that's technically possible. So that's considered very safe. And of course, our ethics board has also signed that.
So it's safe by design. So we can. There's no way to exceed that value. Yeah.
Okay, that makes it easier. I understand it because I just know that ethics boards, in particular, even with measuring skin conductivity, sometimes as soon as there's cable attached to a body, they're getting very nervous. So I was just, and you said, oh yeah, we just need to individually calibrate it for ethical reasons. And I was like, oh, if there's ethical reasons to calibrate it, how do you ethically calibrate it? But I get it, and in particular, if it's, let's say, if it's safe for using it with people, then yeah, you have the safety net there. Cool, thanks. That was cool work all.
Thank you so much.
Yeah, I had a similar question actually. So I thought the calibration and some of the preliminary work you did, you said you were kind of had this pilot study where you determined the axes and how they work. So I'm not that familiar with the prior work, and I was actually really surprised that you're able to come up with these. Both the fact that first you could kind of isolate these axes individually, and then secondly the fact that you could combine them, do this linear combination of the axes. So were you surprised that is this kind of a known thing in the prior work, or were you surprised that you were able to actually do that? This linear combination, isolation of the axes.
This is. I mean, the isolation of the axis so that you only stimulate yaw or only stimulate a pitch. I mean, that's known. That's what the OVR model does. But to this combination, that wasn't known before. And yes, we were surprised by to find that. But yeah, it worked quite well as far as we worked it out. So yeah.
Yeah, I mean that, like I said, that's almost as interesting as the results. So it'd be kind of cool to see a kind of more methodical breakdown of that and some of the limitations of what you can combine and what you can't. So I was also interested in I guess in the simulations you're doing these 3 axes of rotation, correct? And you're applying these to, I guess, the rotational movements of the camera, but there was also some translation movements in the camera. So is it possible with this technique to also stimulate, the effects of translation?
Not so far. So what we addressed in the experiment was only the rotational movements. But what we found, or what also previous work found, is that is not so important. I mean, it can address some cyber sickness, but rotational movements are much worse. And yeah, but no, we cannot address the linear, so the straight linear acceleration so far with this model. But of course, if you drive the slide curve, that is, of course, is addressed. because that's rotational movement, right?
Right. It is, yeah. So I guess in the study, so you didn't reduce. It was actually really interesting how much this. It was surprising for me at least how much the sickness effects were reduced, but you didn't eliminate them completely. Do you think you could eliminate them completely if in a situation where there is no translational movement in the video, or is this just a purely a limitation of the?
That's actually what we want to find out in future work as well. Where does the rest come from, right? So there's some cyber sickness still there. So the question is now, if this only from the translation movements or maybe some effects in the video, for example, it's possible that the lower frame rates, right? The typical video has 30 FPS. But in the VR glasses, we normally have about 100 Hertz. Maybe that affects a little bit of the cyber sickness, but we will research that in the future and hopefully then also reduce that little rest of the cyber sickness that's still there now.
Yeah, okay, great. Yeah, lots of interesting follow-up work to do.
Yeah.
I'm just going to circle back and ask, there's another question for Jan. This one was also from Tobias. So Tobias, do you want to ask this one as well?
Yes, can do that. So basically, I was a bit initially unsure what you wanted to show, but basically, so I know there are these earlier papers that measured, for example, presence questionnaires in VR and outside, so on papers, yeah, and they found no difference. And now you showed that actually even in VR, regardless on how we present it or how we embed it in the game, it also doesn't make a difference, right? I mean, you showed that for presence and you had other questionnaires. So basically, in short, it doesn't matter how we present questionnaires, not how in VR, not outside, it really doesn't matter. Is that the overall conclusion?
I would not say that it doesn't matter how we assess questionnaires. What we focused on is the results of the questionnaires. So maybe we could somehow tone that down for the results or systematic biases in results according to how the questionnaire was assessed. It may not make a difference how we assess it. But I think that we definitely need further research for this because, as I mentioned in the talk at the beginning, this is something that is not really clear in the previous research. So that is, there are some findings that find differences in scores and some don't. But what we in this work did not focus on, but was focused in other works, is that the usability and the user experience when not having to change the actual setting of the task is beneficial for the experience of the users. So I would say it definitely does make a difference how we assess questionnaires, but I think we can be confident to embed questionnaires into VR deeper than by canvases, without having to fear that we have bad results because of whatever negative effects might be there.
I should also say, before I say a completely wrong thing, they showed some small differences, but basically the results were the same. But I think the variance, for example, changed. Yeah. So before, because I said, oh, it doesn't matter. There are some small effects, but basically the main findings seem to be the same. Apparently, that's okay. Thank you.
So I guess I have a follow-up question to this. So I guess in either case, you have the questionnaire, you have a break from VR, and you complete it outside of VR, or you're completing the questionnaire within VR. In both cases, I guess in a sense, there's some effect on presence, because even if you're within VR, you still are aware that you're completing a questionnaire. So I was wondering this is maybe a little bit fantastical to think about, but maybe do you think it's possible to somehow design a questionnaire where participants are not aware that they're filling out the questionnaire? And if you could somehow do that, would this make a large difference in in the effects of the experience?
Yes, that's a very interesting question, and we have definitely talked about that and thought. But what is not very clear to us is if for answering a questionnaire that was designed as a questionnaire where the participant is aware of answering a questionnaire, would be still usable as a validated tool when the user is not aware that he is currently answering a questionnaire. So that's something that needs to be found out first. But I think this is something interesting, and when we think that one step further, this would go into the direction of in time, in real time assessment of psychological factors in VR experience. I think that would be very interesting to develop further. Yes.
Yeah, I agree. Okay, so we have one more question just came in. So this is for Colin. Colin, another question from Jacob Young. Do you see a feasible path forward for this research to be used in real-world scenarios?
What do you mean exactly with real-world scenarios? Like for non-VR related scenarios, or?
I'm guessing that it means that real kind of applications outside of the research lab, outside of studies, and where it's effective and validated, and what are the barriers preventing this from what are the challenges that need to be solved to make this kind of usable in kind of an every day-to-day setting?
I see. I mean, the best thing, of course, would be if it's built in one of the VR glasses in the future. But I think, I mean, I'm not quite sure how realistic that is in the near future. But I think there are some. I mean, from the research point, it definitely makes sense. But I'm not so familiar with all this fabrication processes and stuff, if this is feasible, but of course that would be a huge advantage if it's built in one of the glasses and you can directly address the signals that come into the glasses and look how the content is moving and then stimulate and adjust everything so that the users doesn't get sick in the end. But let's see. Yeah,
I mean, there definitely seems to be some potential benefit there. So there's some value in doing that, I guess. So like we said earlier, a lot of interesting follow-up research questions and more work to be done, I think, before we see that. But I can certainly, it seems like it would be a great feature to have in future displays.
Yeah, probably comes down to a couple of things. Can you still hear me?
Yes.
Perfect. So there's also commercial research on this. So we've seen a couple of projects setting out like 5 years ago to accomplish this, but we haven't seen that come to light so far. So there's probably a couple of engineering questions to solve, like integrating the electrodes properly. You can't just integrate them here in the forehead, but have to integrate it on the back of the head or on the ears. And then every head size is different. So from an engineering point of view and from maybe also an acceptance point of view, that just people are being told, okay, your brain is being fried, basically, that might not be so compelling for the average user. So there's probably a long way to go until we see it commercial setup.
And of course, if you use it like every day, you don't want to use adhesive electrodes, right? So we use this adhesive electrodes and put it on the participant's head and throw it away afterwards. But of course, you don't want to do that if you want to use your everyday glasses and everyday VR experience. So we need a different solution there. I mean, there are other solutions, but this is definitely the least complicated, or this what works best so far. I mean, you can also use, for example, this what you used with EEG, this the gel, right? But yeah, that's also a problem that need to be solved, of course.
Great. So I just have one last question for Daniel. And I'm just kind of curious what you're making of all of this. So with these advances in galvanic vestibular stimulation, do you think this eliminates the need to have discrete navigation? Will this solve the problem, or in other words, is Colin's work making you redundant, or do you think there will still be a need for
hopefully
research? Hopefully.
Hopefully, but my hopes are limited. Let me turn it this way, because I'm doing the other part of the research as well. That's why I'm started to doing discrete things, right? Because I partially gave up, and that's. But hopefully we will find a solution. At one point, I'm pretty sure that we will find a solution at one point. I'm not so sure if it will happen in the next few years. Let me turn it this way.
Interesting. Okay, maybe there's some kind of hybrid solution as well, which would be a future collaboration maybe for next year's VR. On that note, I think maybe this is a good time to wrap up. And it's everybody once again thank our presenters. So thanks for the 3 great talks, and thanks for the questions from everybody, and for the great discussion. That was really interesting, and I learned a lot from this session, and it was great meeting you all. And we will see you all in future sessions.